For the last couple of weeks, we've been talking about equilibria. Last week, we talked about acid-base equilibria. So there's more than just doing regular old acid-base equilibria. Um, you can do other things too, like called buffers. And this is what we're going to be talking about today. We're going to be talking about buffers. That's what the short title is for additional aspects of aqueous equilibria, right? The short title is buffers, right? And uh, let's just talk about what they are real quick. So, hold on one second. Sorry about that. I forgot which button's which. There we go. Okay, so the effect of acetate on acetic acid equilibrium, right? So we remember that acetic acid is the weak acid, right? And when it dissociates, it becomes protons or hydronium ions and the acetate ion, right? So it turns out that sodium acetate, right, is a very strong electrolyte, which is actually funny because acetic acid is a very weak acid, right? It makes kind of sense though because acetic acid is like an organic compound, right? Whereas sodium acetate is a ionic compound, and that's why it's such a strong electrolyte, right? Because things that are strong electrolytes dissolve in water easily, right? Like sodium chloride. So the interesting thing about this is that sodium acetate has the acetate ion, right? When it goes into water, but then also acetic acid when it goes into water has the acetate ion. So these two things have a common ion, right? When you add them to water, and that has some implications. That has some implications. And we'll talk about that in just a second because we need to take roll, and we'll take roll by answering this question here. Which of the following best describes sodium acetate? It's a strong electrolyte. It's a weak electrolyte. It's a middle of the road electrolyte. Or it's not an electrolyte at all. All right, so this was the distribution right here. This was the El Distribuciano, right? The answer was in fact A. It's a strong electrolyte. So uh, I will attribute the fact that three people got this wrong because you're vigorously writing your free labs today, right? But acetate is definitely a strong, sodium acetate is definitely a strong electrolyte. So, um, switching back now, switching back now. So the presence of acetate from sodium acetate in acetic acid will shift the equilibrium, right? Because remember Le Chatelier's principle, you add in some more products, it'll shift the equilibrium towards the reactants, right? And so here, if you add acetate, because acetate is the conjugate base, and it will be the product, right? The product, it will shift the concentration of the acid, the protons, so that there's less protons. Okay, it will make more of the acetic acid that hasn't been dissociated, and that makes sense too because remember that in this equilibrium process, we get to a point where there's there's a certain concentration of protons and a certain concentration of the conjugate base. And if you add more conjugate base, right, then you make it so that it's not equal anymore. The equilibrium is not there anymore, right? And so it's still trying to get back to equilibrium. And so some of these acetate ions will come over and just gobble up these protons or just one proton at a time, right? And in doing that, it makes it so that there's less protons in solution, right? Making it less acidic and making more of the acetic acid that hasn't been dissociated yet. Just remember that when you add in more of the acetate ion, right, we will get less protons because these acetate ions will gobble up all the protons, making more of the acetic acid that is less soluble, right? That is not a strong acid, okay? So what this is called is the common ion effect, okay? We call that the common ion effect. So the formal definition of the common ion effect is that whenever a weak electrolyte and a strong electrolyte containing the common ion are together in solution, the weak electrolyte ionizes less than it would if it were alone in the solution. Okay, so that that obviously affects acid-base equilibria, right? Because in acid-base equilibria, as we saw in the previous slide, you added some sodium acetate into some acetic acid, and you'll get less protons, right? So you'll get less protons. So here's your next question. Here's your next question. Which of the following is not true about the common ion effect? Remember, it says not true. Okay, not true. And per your request, I checked my grammar on these on these answers. Okay, it involves a weak electrolyte and a strong electrolyte containing a common ion. That sounds reasonable, I think. A weak electrolyte ionizes more than it would if it were alone. It affects acid-base equilibria, where all of these are true. All right, so the distribution here is this, and the vast majority of you got that correct. The answer is in fact B, right? Exactly. See, I knew somebody was paying attention, even though she's vigorously writing her pre-lab. She's paying attention, right? Anyway, so here's an acid-base example then, right? If I were to have a pH of a solution, what is the pH of a solution, right? That's made by adding 0.3 moles of acetic acid and 0.3 moles of sodium acetate to enough water to make a 1 liter solution, right? So again, we have our acetic acid right here, okay? And then we have our protons there, our H3O, hydronium ions right there. And then we have our acetate, okay? And remember that the Ka equals the products, which in this case are the protons and the acetate ion, divided by the concentration of the acetic acid itself. And we already know from a chart that the Ka of acetic acid is 1.8 times 10 to the negative 5, right? So all that stuff you already know. So here's the new stuff right here, okay? Since we have a common ion now, right? Instead of the ice table being 0.3, 0, and 0, what do we have now that's different? It's going to have 0.3 here as well for the acetate ion, right? And the reason why it has 0.3 on the acetate ion is because remember that the problem here says that not only do you have a solution of 30 moles of sodium acetate, you also have a solution of 30 moles, 0.3 moles rather, of acetic acid. So you have to take into account the 0.3 moles of the acetic acid as the initial, and you've got to take into account the 0.3 moles of sodium acetate in the initial. Okay. So that changes then our equilibrium equation just a little bit, right? We still have the same change. It's going to be minus x plus x plus x, right? The equilibrium equation for the acetic acid will be the same, 0.3 minus x. The protons stay the same too, so it's just x. But now on the acetate ion side right here, right, it's going to be 0.3 plus x, okay? 0.3 plus x. So that's the difference in the ice table now. That is the difference in the ice table now, okay? So continuing in this example, right? Continuing this example, we have all this stuff happening here, right? Where we have the Ka, right? And then from the ice table, X is the hydronium ion or the proton concentration, right? And then the 0.3 plus X is the concentration of the acetate ion, right? And then that's all divided by the acetic acid, which is 0.3 minus X from the ice table. And once again, this is a you welcome moment, right? Since we're doing acid-base equilibria for a weak acid, it's so weak that the change in X for a plus or minus, right, is so low that we can just drop the X, right? So I think that Ms. Dickens said that in discussion yesterday, and then she came to me and asked me what that meant or something. But yes, if you're doing chemical equilibria, which is the chapter we did before this one, then you have to do the quadratic equation. But if you're doing acid-base equilibria, you can just drop the x. That way you don't have to use the quadratic equation, right? So all that leaves you with, then is, you see how over here we have the Ka, and then the 0.3 here, the plus x is gone, and then over here the minus x is gone. So that just gives you x times 0.3 divided by 0.3, right? And then x then equals 1.8 times 10 to the negative 5. Why? Because these numbers cancel out, right? Those numbers cancel out. The 0.3 cancels out. Again, you're welcome. I know you're not really seeing that yet, but you're welcome anyway. Okay? Because look, there's like no math to do at all because they cancel, right? So they cancel. And so literally X is just the Ka now. And that means then X, the Ka is the hydronium ion concentration now, right? And then for you to be able to get the pH, all you have to do is take the negative log of the hydronium ion concentration or the proton concentration, and you get it to be about 4.74 as pH. Okay, so in this particular example, right? In this particular example, those numbers did cancel out because the zero point 0.3 was the same for both the initial of the starting acetic acid and the acetate ion, but it could be different next time, and you won't have these numbers be the same, and they won't just cancel out. You might actually have to do some rudimentary math, like multiply both sides by the bottom number and then divide, that kind of thing, right? Or do a cross multiplication, whatever. By the way, that's the same thing as cross multiplication. Doing multiplying by both sides the same number is the same thing as doing cross multiplication, right? So does everybody get what's going on up there, right? The only difference, thank you. At least you're being honest when you go, yeah. Don't worry, we'll talk about this again. But the only difference now, since you have a common ion, is that instead of just having x there, so it becomes like x squared, you have an extra number there now, right? That's the big difference. Okay. So again, the same thing can happen. The same thing can happen with the base too, right? So here we have an example of ammonia being added to water, which gives us the ammonium ion and hydroxide, right? And when you add more hydroxides, right? Oh, sorry, not hydroxides. Add more ammoniums. If you add more ammoniums, it makes it so that the hydroxide concentration goes down, right? Because the equilibrium shifts to the left towards the reactants again. So the same thing happens with bases. And you can still do the problem the exact same way, right? Instead, when you're working with bases, what do you use instead of Ka? Yes, Kb, exactly. See, look at her. She's paying attention, sort of. I like how you look around like, am I paying attention? As long as Dr. No thinks I'm paying attention, that's all that matters. Right. So, this is your next question. This is your next. See, this is how I keep you. Yeah, because I knew you guys would be doing this today, so I'm trying to keep you involved. Huh? It's okay. Weird. Really? That's okay though. But yes, there's. I knew this is what most of you would be doing. That's why I added so many questions to keep you involved. Yeah, no problem. All right, which of the following is true about the weak acids, about weak bases and the common ion effect? The common ion effect applies to weak bases the same way. That seems reasonable. The solution contains a weak the solution contains a weak base and the salt of a conjugate acid. Sounds reasonable too. And then the base won't dissociate as as much as if it were alone. Everybody's answered. Good, good, good. See, I'm so proud. Maybe we should do this all the time. Have you writing stuff while I'm teaching, right? Imagine that, taking notes, maybe. That's crazy. No, I'm kidding. The answer is in fact D. All those are true. All those are true. Um, the all those are true, and they do apply to weak bases the exact same way. This time it's going to be a weak base and the conjugate salt of the salt of the conjugate acid. This time, because it's not an acid, it's going to be the conjugate acid. And then remember, in the one that was about weak acids, it was like will be more, right? But this one is will be less, so that's correct. And so all of these are true. What are the situations in which you have a common ion, right? And the common ion makes it so that practically when you're working these problems, you have instead of having 0 for initial products, you'll have some, you know, something in there for the initial products, which you work them all the same way anyway, right? So for the KPs and for the KCs, you've got to use the quadratic equation. But for weak acids and weak bases, you can just use the drop the minus x method, right? Drop the minus x method. Not dropping x, but dropping the minus x, right? So you still have the x squared, right? You still have to do that, but you can drop the minus x. So when you have a common ion in a solution, right? And what happens is that when you have a common ion in a solution, it does this thing called the common ion effect, right? Which is what we talked about last week, where the common ion effect makes it so that there would be uh, less solute dissolved, right? It would be less ionizable, right? And so this effect is actually called a buffering effect, okay? And so now we're going to be talking about buffers. And so buffers, right, are solutions of weak conjugate acid base pairs that resist drastic changes in pH. These are called buffers, right? These solutions contain relatively high concentrations, uh, 10 to the minus 3 molar or more of both acid and base, and their concentrations are approximately equal. So what you actually see in this picture here are actually buffer standards. We use these a lot in chemistry. If you ever used a pH meter before, like a pH pen, and you stick it in there, it tells you what the pH is, right? For those things to know what pH is what number is what concentration is what, you have to actually use these things. So usually it's like pH 4, 7, and, oh, sorry, that says 4. 4, 7, and I think that says 10. I can't really read it, but those are normal. And so you stick the pH meter into the buffer solution, and you tell the pH meter, this is what it looks like to be pH 10, right? And then it goes, okay. And then you can do it again for this is what it looks like to be pH 7, and you do it again, this is what it looks like to be pH 4. And so the way that pH meters work is that they are able to tell pH, which is hydronium ion concentration, by the electrical current, right? That's that's conductible inside the solution, right? So that's how it tells. And so these buffers will actually at these certain pHs will give a standard reading for the pH meter to know what the current will be at 4, 7, and 4, 7, and 10, right? And you want to do that because the pH range is 0 to 14, right? But you want to you want to use standards that are in the middle, right? You don't want to ever one thing that you'll learn a lot in analytical chemistry, forensic sciences, all kinds of stuff like that, is that you never want to measure anything at the extreme. Okay. So, for example, if you're using a pipetter that is 1,000 milliliters, or sorry, microliters, you never ever want to go all the way up to 1,000, right? If you're going to do that, you might as well use a 2.5 mil pipetter type of thing, because we find that at the edges, at the extremes, it's very inaccurate, right? And so it's the same way with pH. We don't want to put standards at the edges, right? We want to put them in the middle, because the vast majority of the solutions that we talk about are going to be like this, unless you're going to be why would you put, like, a pH meter into concentrated sulfuric acid that's going to be less than 0 pH? That would just not make any sense at all. Um, so that's why a lot of people ask, why do we only use 4, 7, and 10? It's because you never want to do a standard that's at the edges of the actual range of what you're reading, right? So how do we make a buffer? How do we make a buffer? We make a buffer, number one, by mixing a weak acid and the salt of its conjugate base, right? Sorry, the salt of its conjugate base, or a weak base and the salt of its conjugate acid. So the prime example of this, right, we use in biochemistry a lot is phosphate, right? We use phosphate buffers. We call it PBS, right? Phosphate buffers. That actually is PBS saline, so it has the S stands for saline, some salt in it too. But the way we would do it is we'd have phosphoric acid being the acid, right? And then we would have phosphate ion being the conjugate base, and that phosphate ion comes in the form of sodium phosphate, right? Another one that people use a lot too is acetic acid and sodium acetate, because acetic acid has the acetate ion. So the common ion there would be the acetate ion from sodium acetate, right? Those kinds of things, okay? And then you add a strong acid, particularly a strong acid, and particularly neutralize the weak base, or add a strong base to partially neutralize the weak acid. Okay. So when I was telling you that a second ago, I was saying how we use sodium acetate or acetic acid, and then we had phosphate and the phosphoric acid. The phosphoric acid in that case would be the strong acid, right? So it's interesting stuff. How does a buffer actually work? All right, how does a buffer actually work? Well, uh, practically what it does is that it makes it so that there's not huge changes in pH, right? And the one most common, and you carry it around in your bodies all the time, right? And it's the reason why you're alive right now. And it's called the carbonate bicarbonate buffering system in your blood. And I think I've talked about this before, but just to reiterate again, your blood has to be an exact pH of 7.4, okay? If it's any higher than that or any lower than that, you could get really sick, okay? It could kill you, actually. And so the way that your body actually maintains that pH of 7.4, right, is by using what we call the carbonate bicarbonate buffering system, which actually uses carbonic acid, right, and the carbonate or bicarbonate base, conjugate base, right? And it goes back and forth, making sure that your pH is 7.4 in your blood all the time. Um, and so, and if you think about it, if you have a a solution that's 7.4, right, and there was not any buffering action, and you add in, you get, let's say you drank something super acidic, right, like orange juice, for example, right? You know something that's super acidic like that, right? Or you ingested something that was super acidic, it would immediately change the buffering, change the pH in your system, right? And if it changes too much, you could get sick. So that's why we have a buffering system in our bloodstream. And so in this case, say you drink something acidic, and I'm telling you this is very rudimentary right here. This is not like exactly how it works. But say you consume something acidic like orange juice or lemon juice or something, tomato sauce, that's also very acidic too. Coca-Cola is very acidic. Um, and and then it gets into your bloodstream, and then you have in there the carbonate ion, right, which is the conjugate base, right? It can accept that proton, and when it does that, it makes it so that when the proton's being accepted by the carbonate ion, it doesn't float around free in your blood, and it's when it's free floating around in your blood is when your acidity goes up. Does that make sense? So basically, what a buffer does is that it has free conjugate base is floating around, and it will, and then when you add an acid, right, it will grab those protons from that acid so that it doesn't stay in solution, making your acidity go up. Does that make sense? Right? And the same thing can happen in the other direction too. It can get more basic as well. Okay. And we saw in the previous slide, right, that our previous lecture, that not only does your blood need to be a certain pH, right? Your intestines have to be a certain pH. Your stomach has to be a certain pH, right? It's especially important in your intestine because you have bacteria in your stomach, right, that are actually involved in your digestion. And if it gets too acidic or too basic in your intestine, right, you kill off that bacteria, and then you're really, get some gastrointestinal issues now, right? So let's talk about then how this works chemically, right? So I use carbonate as an example because that's in your blood right now, the carbonate bicarbonate buffering system. But here they're using the fluoride ion as the buffer. Okay, so here's a solution, right? And if you have in here, right, if you have in here hydrogen fluoride, right, some of it will be some of it will be hydrogen fluoride, and some of it will be the fluoride ion, right? Some of it will be the fluoride ion, okay? And the interesting thing, or the thing that's very helpful here, is the fact that when you have, like, in a buffering system of fluoride, and you add some protons, right, which makes things more acidic, you get more hydrogen fluoride, right? It used to be equal right here, right? It used to be HF is equal to the concentration HF is equal to the fluoride ion. But since there's a buffering system in place where we have an excess, not an excess, but like we have fluoride ions almost in the same concentration as HF, you can add more protons and then the hydrogen fluoride concentration goes up, right? And then the fluoride concentration goes down, but it doesn't change the pH because the protons aren't freely floating around, right? If the protons are freely floating around, that's when your pH would go down or your acidity would go up, right? And it happens the same way on the other side too, right? Again, we have here a concentration of hydrogen fluoride, and then we have the fluoride ion, okay? But if you add in some hydroxide, okay, then the hydroxide will pull off the proton from hydrogen fluoride, making water, okay, and then making more fluoride ions, but neither water nor fluoride ions actually increases pH, right? Does that make sense? You have ions in solution that can either occupy protons or occupy hydroxides to maintain the pH in a buffer, okay? It maintains the pH in the buffer, right? So adding a small amount of acid or base will only slightly neutralize one component of the buffer, so the pH doesn't change much, okay? This is actually a pretty cool slide here, or a pretty cool diagram here, okay? Pretty cool. So your first question today is this: which of the following is not true about buffers? They are strong solutions. They are solutions of strong conjugate acid-base pair that resist drastic changes in pH. That seems reasonable. They can be made by mixing a weak acid and a salt of its conjugate base, or a weak base and a salt of its conjugate acid. It can be made by adding a strong acid and partially neutralizing the weak base, or adding a strong base and partially neutralizing a weak acid, or dang, my laser died. Or adding a small amount of acid or base only slightly neutralizes one component, so the buffer doesn't change much. Dang it, my thing died. So sad. I wonder if there's a way to charge it real quick. And I got logged out of this thing. Very frustrated getting logged out. There you go. Forms. This one is a tricky one. There's a lot of words there, so I don't blame you. Leave. Let me find this here. Okay. Still waiting for a couple more people. Talk about it if you need to within your group. Okay. Okay, so the vast majority of you got this one correct. Very good job. I wish I could point at it, but I don't have a laser, so I can't. The answer is, in fact, A. It should be a weak conjugate acid-base pair. It should be a strong. Okay, so good job there. This is really inconvenient that I have to use a meter stick now. I'm glad it's here, but it's very inconvenient. Okay, so let's do a little quick review. Right here, if we have a weak acid, right? For weak acid, if we have Ka, that equals the hydronium ion concentration or the proton concentration times the conjugate base divided by A, right? So say we need to take the pH, we have to figure out what the pH is of a buffer, right? What you need to do is take the log, the negative log of the Ka, right? And take the negative log of this side as well, right? Take the negative log of that side as well. So you have this now, right? Okay. And then you can rearrange the equation now so that it says the negative log of the hydronium ion concentration, right, equals the negative log of the Ka plus the log of the conjugate acid divided by the regular acid, right? And something should already look familiar to you, and it's this right here. What is that right there? Exactly, that's pH, right? That's pH. So all you need to do is plug in the Ka, plug in the concentration of the conjugate base, plug in the original concentration of the acid, and you get pH, okay? And this is actually a very, very common equation, right? Oh, by the way, does anybody remember what P stands for? I talked about this before. Huh? Huh? Say again? No, no, oh, no, 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 no. P, the letter P, when you put it in front of anything, what does it mean? Say again? You do know. No. Give you a hint. Okay, I'll give you a hint by going backwards. Look, okay? So if the negative log of the hydronium ion concentration slash proton concentration is the pH, right? What does the P in pH mean? We already know that the H in pH means what? Proton, right? So what does the P part mean? Yes, exactly. When you see the negative log of anything, it really means P, right? It's P, okay? Does that make sense so far? It's just the chemists are like, they're lazy, so they don't want to write out the word negative log. So they just, they say, okay, negative log means P. So that's why it's pH. It's short, right, for negative log. Okay? That's why this is pH. Remember pH equals the negative log of the hydronium ion concentration, right? Does that make sense already yet? Yes? If pH is the negative log of the hydronium ion concentration, right? And the H part of pH is the hydronium ions, then what does the P part mean? Negative log. I mean, it's possible. They are German, actually. Most chemists are German. The early chemists, right? I know it's crazy, but yeah. So if you have the negative log of the hydronium ion concentration or the proton concentration, they mean the same thing, right? This negative log here is just P, okay? People just say P, lowercase p, right? And this part here is the H, right? So you put it together and you get pH. And the reason why you do that is because this number is usually a very difficult number to deal with. It's always a number that's a hydronium, it's always a number that's a scientific notation number, right? And so when you take the negative log of anything, it turns something that's a scientific notation into something that's in between the numbers of 0 and 14 for pH, right? Does that make sense? Okay, so if this is pH, right? Negative log of the negative log of the proton concentration or hydronium ion concentration is pH. What do we think we change this to here? The negative log of Ka. Say that again. Say that again? Yes, pKa. right? This is pKa then, okay? So one of the things you'll learn, especially when you go through analytical chemistry, biochemistry, all those other chemistries that you might have to take later on in life, organic chemistry, pKa is actually what we use in chemistry to determine how acidic something is, okay? So the smaller the pKa, the more acidic it is. The bigger the pKa, right? Sorry, let me say that one more time. The smaller the pKa, yes, that's right. The smaller the pKa, the more acidic it is. The higher the pKa, the more basic it is, right? Or the less acidic it is, okay? And so, for example, now we have this equation, right? I don't know why I said example. So now that we figured that out, we have this equation where pH equals pKa plus the log of the acetate divided by the original acid concentration. And this is an equation that you'll use a lot in life, right? Especially in the next few chemistry years, semesters. It's called the Henderson-Hasselbalch equation, okay? So the only reason why I went through all that was just to show you where that pKa came from, right? It literally just means negative log of the Ka, right? Does that make sense? Do you know why we change it to pKa like that? It's because usually when you see a Ka, isn't another number that's like got a scientific notation in it, right? So chemists want to make it easier by just getting negative log, and then it becomes like a whole number, you know? So you'll see pKa's that are from 0, which are the strongest acids, like sulfuric acid, things like that, all the way to 50. And 50s are very weak acids, are very strong bases, right? So this is the Henderson-Hasselbalch equation, okay? So if you have a Ka, which oftentimes you have a Ka, because you can look that up on a chart. Remember that, right? Remember that chart I showed you that had a list of all the known Kas? Okay? So if you get a question on an exam that has you might have to figure out what the conjugate acid is, right, from the ICE table, but you'll always get the initial concentration, right? And then you have the Ka, right? The Ka from a chart, or it's going to give it to you in the question. Then all you have to do is plug all that stuff in, and you'll get the pH of a buffer, right? The Henderson-Hasselbalch equation is quite useful, okay? Quite useful. So you can see why I don't want to put this onto the I didn't want to put this on the next exam, because you're not going to use it at all in the next exam. It'd be very confusing to have both. So here's an example, okay? Say I have a solution, a buffer, that is 0.1 molar lactic acid, right? And then, which is this formula right here, lactic acid. And then I have 0.10 molar sodium acetate. I'm sorry, sodium lactate, right? And I have a Ka, right? I have a Ka that is 1.4 times 10 to the negative 4, right? What is the pH of the solution, right? What is the pH of the buffer? So it's really simple, right? Because you're usually given a Ka, or you can find it in a chart, okay? And then you're given the acetate concentration, which is 0.1, goes at the top, right? And then you get the initial concentration of the acid, which is 0.12, put it at the bottom, right? And then all you have to do now is go 3.85 plus, this part here is the 3.85 part, right? And then we have minus 0.08, which is a log of this part right here, and then you get a pH of 3.77. No ICE table needed, right? No ICE table needed, okay? Isn't that cool? No ICE table needed. Huh? Anybody have any questions about this example? It's pretty easy. Yeah. Yeah, that is a good question. Yes. Yes, that is a very good question. Okay, HA is always going to be the unionized acid, right? So it will be always be called lactic acid, okay, or some kind of like acetic acid. It will always have the acid in its name, right? And then the conjugate base here, A minus, will always have an 8 at the end because it's an ion, right? It's a negatively charged ion. So it'll always have an 8, right? So for the purposes of this particular kind of question, always think that the one that says acid is going to be at the bottom, right? And the one that says 8 will be at the top, okay? Make sense? Good stuff, good stuff. Don't worry, we'll get more a little bit deeper into this on Monday, or not Monday, Wednesday, but because class is almost over for right now. But this is what I really wanted to show you before too long, which was this, the Henderson-Hasselbalch equation. Okay, so a couple more slides. Let's get to the next question, and then we'll go over to do discussion, okay? Which is only 2 more slides. So what is buffering capacity, right? All this here just says this one thing. Most buffering capacity is going to be plus or minus 1 pH unit, okay? So for example, if you're talking about the carbonate bicarbonate buffering system in your blood, and your blood is pH of 7.4, the buffering capacity of the 7.4 in your blood is plus or minus 1 pH, right? That means it can handle, right, protons and hydroxides up to 6.4 pH or 8.4 pH, right? Plus or minus 1 pH. Does that make sense? That's exactly what that says up there. In a lot of words, it says that, okay? Buffering range is plus or minus 1 pH, okay, unit. The vast majority of them are like that, okay? Any questions about that? Is that confusing at all? Okay, so this shows you why. That's a that's a that's a typo. That should be a lowercase p right there, right? But the range of a pH value over a buffer, over which a buffer system works, is effectively the optimal pH where the concentration of HA equals the concentration of A minus, right? So if one concentration is 10 times more than the other, the buffering range is 4. This means that the pH range of a buffer is usually what? 1 plus or minus 1 pH units. Does that make sense? When we have buffers, we can do things like add strong acids, right? Or a strong base to a buffer. And what's supposed to happen is that the pH shouldn't change that much, right? The buffer has a 1 pH unit buffering region that keeps it so that there's not these big pH changes, right? So the addition of strong acid or base is a neutralization reaction. You can calculate the stoichiometry problem to find the concentration of the acid and the conjugate base when all of the acid or base reacts, right? And then to do that, we'll to find that pH, we'll use the Henderson-Hasselbalch equation, right? Because all you need for Henderson-Hasselbalch is the Ka and the conjugate base over the acid, right? Or the base over the acid, okay? So this is this week's you're welcome chart right here. Sort of, not really, I don't know. But it tells you what happens, right? Or the equation you should be using when you add in, right? Either a strong acid or a strong base, okay? So here, if you add in a strong acid, right? The equation you should be using here is the HA, oh, sorry, the conjugate base plus the proton makes HA, right? So strong acid reacts with the conjugate base component of the buffer, and then you can calculate the new HA and H minus, right? And from that, use the Ka and all calculate to get the pH. On the other hand, if you're doing a strong base to a buffer, right, instead of using A minus and H plus, your equation will actually be a little bit counterintuitive, but it will be the acid plus the hydroxide goes to A minus to the water and plus the water, right? And the reason why that is because the strong base reacts with the weak acid component of the buffer, right? The weak acid component of the buffer. So that's that, HA right here is the weak acid component, okay? And then once you get that, you can use that for stoichiometry to get your concentrations that you need to get to the pH from pKa, okay? So, and don't worry, there won't be a lot of these questions today because I have to get through a lot. But here's your first question. When a strong base is added to a buffer, what happens? It reacts with the conjugate base component, it reacts with a weak acid component, it reacts with the water component, or it reacts with nothing in the buffer. All right, so the answer to this here, anybody want to say it? Did you know? Yes, it is in fact B. The strong base will react with the weak acid component of the buffer. Yes, yes, very good. Has everybody scanned just to make sure we have attendance? Yes, good. Okay. All right. So here's an example of a buffer calculation. We've got a buffer, and it's made by adding zero point 0.3 moles of acetic acid and zero point 0.3 moles of sodium acetate, enough to make water, with enough water to make 1 liter, right? So calculate the pH after you add in 0.02 moles of sodium hydroxide. So this is a very simplified way of asking this question, okay? Most of the time what will happen in the questions that you get, like from the assignments and the exam and stuff like that, it won't give you it in moles, right? What you're going to have to do is actually, it'll give it to you in molar, and you have to convert it to moles, right? So remember that moles is equal to the number of moles, sorry, molar is equal to the number of moles divided by 1 liter. And one of the reasons why it's already in moles that easy is because you made it 1 liter, right? But it's never going to be that easy. You're going to have to remember to convert to moles, okay? So in this particular problem, again, we start out with the acid being acetic acid, 0.3 moles, right? And we also start out with 0.3 moles of sodium acetate, right? And we're going to add to it the sodium hydroxide, 0.02 moles. So we, of course, come up with our ice table here. And since we did a strong acid, right? We did a strong base plus a weak acid. We start out with, that's going to be our equation. So here's our equation right here, our weak acid, our strong base, and it becomes water and the conjugate base, right? Just like it said in that little you're welcome chart I gave you a second ago, okay? And so the biggest change here though, is no longer do we see equilibrium here, we see after the reaction here now, right? And instead of seeing initial here, we see before the reaction. So before the reaction, the buffer had uh, 0.3, right? It had 0.3 of the acetic acid, 0.02 of the hydroxide, and at the end, and on the other side, it had the 0.3 of the sodium acetate, right? The sodium acetate, which was the buffering agent, okay? And so, what's the change going to be? Well, when we add in the 0.02 moles of sodium hydroxide, we lose those moles of sodium hydroxide because they pull off protons from the acetic acid. So you'll lose the exact same number of moles of sodium hydroxide that you put in, and you'll also lose the same number of moles of acetic acid because the acetic acid became what? The acetate ion, right? And that's why on this side, you get 0.02 moles more of the acetate ion. These 0.02 moles of the acetate ion, right, came from the fact that these 0.02 moles of hydroxide pulled off 0.02 moles of protons from the acetic acid, okay? So it's simple arithmetic now, okay? Simple arithmetic, this minus this gives you that, right? This minus this gives you 0, this plus this gets you that, right? And so now after the reaction, you have 0.28 for the acetic acid, and you have 0.320 for the acetate ion. And Mary, I have wonderful news for you. We have decided to move the due date of the report to Friday at 11:59 p.m. So I should have had you guys do the end of course evaluations today. Anyway, I'm just kidding. Okay, totally kidding. Oh, that reminds me. Um, don't tell me your name. I just said it. Kimberly. You were not here on Monday. You have to do your end of course evaluation. We'll do it later though, like during lab, because there's still few people in here that haven't done it in lab. Okay, so of course, what do you do now? You've got your. So now that you've done this kind of modified ice table, you've got your number of moles of acetate, and you've got your number of moles of acetic acid. You plug it into the Henderson-Hasselbalch equation, right? You have a Ka because you know what the Ka of acetic acid is. You can get that from a chart, and then you can plug in the acetate concentration here or number of moles here, and then the acetic acid concentration there or number of moles there, and this is what you get. So one thing you do need to pay attention to here for all of you that are actually writing your pre-labs, this is a typo. This should not say number of moles of HA. That should say number of moles of A minus. So that's a typo. Fix that in your notes. So so that when you're doing your notes, you don't get confused. And then over here, there should be number of moles of HA, not A minus. Okay. The book publisher screwed that one up there. Okay. So just make sure you know, right? Because it's always going to be the base over the acid, right? It will never be the acid over the base. So make sure you have that clear. Okay? Huh? Yeah, it wouldn't make sense, right? Exactly. So, quite easy. Plug in the Ka for acetic acid there, take the negative log of that thing, you get 4.74, and then take the log of the 0.32 over the 0.28. Again, those numbers come from this ice table, right? 0.28, 0.32, right? And you get a pH of 4.8 for the concentration, sorry, the pH of that buffer that we just talked about, okay? So now we can talk about how mixing things together will change the pH and stuff like that, right? So here we start out with 1 liter of buffer. It's 0.3 of the acetate, 0.3 of the acetic acid again. We know it's a pH of 7.4. Interestingly enough, we added in sodium hydroxide to that same thing earlier, didn't we? And it only went up to 4.8, right? Isn't that crazy how a buffer, oops, went the wrong way. Isn't that crazy how a buffer keeps it from changing pH, right? Crazy. And we added in like a lot of sodium hydroxide, right? That's crazy. Strong base. So buffers really do work. Sorry. So we added in this 5 mils right there. Sorry. So in this picture, right, we have 0.3 of each, the acetic acid and the acetate within the 1 liter buffer. We can add in 5 mils of 4 molar sodium hydroxide. That's pretty concentrated, and it brings us to 4.8 pH. It increases the pH by 0.06 units, almost nothing. And then we have water now. We got a liter of water, right? And then we add a liter of water. Water is semi-acidic, right? And so, what am I saying? Water is not semi-acidic. Is water no semi? Water's neutral. My apologies. Anyway, we have our water. If we just have water at pH 7 and we add in 5 mils of sodium hydroxide, it immediately increases the pH by like 5.3, right? Units. So you go from 7 pH to 12.3 pH. Sorry, there's like a little glare on me. I couldn't read what the number said, right? So notice how you have a buffer here. You add this amount of sodium hydroxide, it only goes up by 0.06 units. But if you just have water with no buffering in there, right, the base will immediately increase the pH by 5.3 pH units, right, all the way up to 12. Now you have a very basic solution. Cool stuff, right? So what is the pH of 5 mils of sodium hydroxide? 4 molar sodium hydroxide is equal to 1 liter of water. You see it there, right? And then what if 1 liter of buffer what if it's 1 liter of buffer? And then you see that right there, right? Cool stuff. Cool stuff. Good stuff, right? So I can show you now how these calculations are done. Okay, so here we have our 5 liters. 5 liters. Was it 5 liters? 5 mils, wasn't it? 5 mils of water, right, times the 4 molar, right, gives you this number of moles of sodium hydroxide, right, and then you have to get the total volume. So it's the 1 liter plus the 5 mils gets the total volume of the solution. Divide that by the number of moles, and then you get the new molarity, which is 0.00199 molar sodium hydroxide, right? And quite easily, all you do is do the POH and then you do the minus of the pH. You get the POH, and you subtract it from the pH. I mean, sorry, from 14 to get the pH, right? And that's how you get that number. So it's really easy to do those kinds of calculations. Really easy. So remember, you had this number of moles, 2 moles of sodium hydroxide added right there, right? So you add into the 2 moles of sodium hydroxide. I got a little confused because it said 2 times 10 to the negative 3, but that's really just, yeah, 0.002. And so if you have that there, what happens is you lose 0.002 from the acetic acid and you gain 0.002 from this acetate, right? Because the hydroxide pulled off the protons from the acetic acid to make the acetate. So just basically doing the ice table in your head, right? If you started out with 0.3 moles of acetic acid and you have 0.002 moles of hydroxide, it will pull off 2.002 moles of of the proton from the acetic acid, giving you 2 extra moles of the 0.002 extra moles of the acetate. So, same as before, we can pull this into the Henderson-Hasselbalch equation. This is the the Ka of acetic acid, 1 times 10 to the negative 5. Take the negative log of that, and then you do the positive log plus the log of the ratio of the acid, the base divided by the acid, right? And so 0.302 divided by 0.298, and you get 4.75 as the pH, which is the original buffer. So sorry, which is the new pH when the original buffer was at 7.4. So you only moved up like 0.01 here, right? So kind of neat, right? Very, very small change because you have a buffer, okay? So we already did a titration in lab last week, but we'll do another one today where you actually will get to use a pH meter, right? If you did your pre-lab exercise and wrote out your instructions, you saw that we have a pH meter this time, right? So basically, we already know what's going on here. We have like an unknown concentration of acid down there. We have a known concentration of base. We titrate it till it gets to the end point, that point where it's slightly pink, not too pink, not fuchsia, right? And then you can do some molar stoichiometry math to figure out what the concentration is of the unknown acid based on the concentration of the known base, right? But except in the last lab, you won't have to do this in today's lab. In the last lab, you had to actually start out by titrating the KHP first because it was a solid, right? To get what your hydroxide concentration first, and then you use this hydroxide concentration that you just figured out from the KHP to titrate the acid, the unknown acid, right? And then that's when you actually get to the titration of the unknown acid part, okay? So a pH meter or indicators are used to determine when the solution has reached the equivalence point, the amount that the acid equals that of the base, right? And that's that point you saw when it was turning slightly pink. When it goes too pink, then you've gone past the equivalence point. So what happens when you titrate a strong acid with a strong base, which is basically what you did in the last experiment, right? It starts out like really low over here, right? So we have pH on the y-axis, and we have mils of sodium hydroxide on the x-axis, right? And as you can see, right? So a lot of you guys, when you were doing the titration, you weren't seeing anything turn pink, right? You're like, what's going on here? Nothing's turning pink. Well, it's because it actually starts out super slow, right? At the very beginning, when you have an acid, it starts out super slow, right? And it doesn't start turning pink until it gets to up around here, right? So that's the big key point, right? From the start of the titration near the equivalence point, the pH goes up really slow, right? And why is that? That is because you're starting out with hydrochloric acid, it's floating around in the water, and then you add in the sodium hydroxide, right? And the sodium hydroxide starts to interact, right, with the acid, making the sodium chloride, right? But it doesn't actually do that. It doesn't actually make it in an appreciable amount till you get close to the equivalence point, which is right here. And so you notice once you get to the equivalence point, right, you have this really straight line, right? A very straight line that goes all the way up to pH 12. So notice that the reason why when you go past the equivalence point, basically get into a fuchsia color, right? You've kind of messed up a little bit because it doesn't take much, right, to go from the equivalence point all the way to, to pH 12. You're no longer, because you're wanting it to get to pH 7, right? That's the equivalence point. It doesn't take that much to get it all the way to pH 12, right? So that's 10 mils right there, right? It takes like less than 1 mil for you to get from pH 7, right, to um, pH 11, right? And so that's why when we tell you to do the titrations and you're dropping the phenolphthalein, I mean the hydroxide into the acid, and the phenolphthalein is turning pink, right? We want a very, very, very light pink color, right? And even if it goes away after a while, you're probably better off leaving it at that light pink color and letting it go away than adding 1 more mil, as many of you saw. When you added 1 more mil, it shot straight up to pink, right? To fuchsia, okay? And so over here, it levels off after you get to the equivalence point to about pH 12, right? But the important thing to note here is that at the equivalence point, there's a very rapid rise, right? A very rapid rise. Before it, very slow. After it, it levels off. So the equivalence point is where we want to get pH 7, okay? Good stuff, right? So here, this is clearly important since I have a slide just about it. At the equivalence point, the pH is 7. As more base is added, the pH levels off again, so it slows back down again, right? So this is interesting, right? Let's do it the other way, right? Say we started out with a strong base, okay? And now we're titrating into it a strong acid. The same thing happens, right? The same thing happens you are where you are starting at a very high pH, right? And you add in the acid, and it really slowly goes down, super slow, until you get to almost pH 7, or to the equivalence point, right? And right at the equivalence point, right, it only takes less than 1 mil of water to get you from this point to this point, and you're fully acidic again, right? So it's literally the exact same thing. Titrating a strong acid with a strong base, right, is the exact same thing as titrating a strong base with a strong acid, just backwards, right? So yeah, so just remember that, at this point here, right, we have a pH that's less than 7. Over here, we have a pH that's more than 7, and here we have a pH that's 7. Okay, for both of these guys. Okay, for both of these guys, depending on what the graph looks like, which is what you'll be doing today in lab. Actually, you're going to be doing this titration where you are going to plot these points using the pH meter and actually do this. And so that's why you actually need a partner for this lab, because one of you will be doing the titration part with the burette. We're going 1 mil at a time. And then when you get to close to the equivalence point, right, you're going to go and do 0.4 mils or a quarter of a mil at a time. And the whole time that you're letting 1 mil down and closing, 1 mil down and closing, your partner is going to be writing down the pH that's on the pH meter, right? So that's why you need two people to do this experiment. Does that make sense? There is an odd number of people in here, so there might be a group of 3. Is there an odd number of people? Is there anybody missing 4, 6? Yes, there's 11 people in here. Okay. Oopsies. So here's your next question. At the beginning of a titration, what happens to the pH? At the beginning of a titration, what happens to the pH? Okay, so what is the answer to this one? Does it rise slowly, lower slowly, rises fast? A, exactly, it rises very slowly. The pH rises very slowly, right? Good job, good job. So let's keep on going, all right? So let's say we're titrating, let's talk about titrating weak acid with a strong base, which is what you'll be doing in lab today too, right? You can use the Ka to find out what the initial pH is, right? And so here, it's very similar to what's happening with the strong acid strong base, but notice that the equivalence point part is much smaller. It's much shorter. Okay. So find the pH find the pH in the buffer region using the stoichiometry followed by the Henderson-Hasselbalch equation. And at the equivalence point, the big thing here, okay, the big thing here is that at the equivalence point, the pH is actually greater than 7, because the conjugate base of the weak acid is used to determine the pH, right? So the thing I want you to take away from this particular slide here is that when you titrate a weak acid with a strong base, unlike in strong base, strong acid, where the pH is 7 at the equivalence point, here with a weak acid and strong base, the pH is going to be greater than 7, right? It's going to be greater than 7, okay? So you can see how the equivalent points here is actually at like, what is that, 8 point, 8.5 or something, right above 9, right? Right above 9. So as more base is added, the pH level's off, and this is exactly what happens for strong acids, right? So the only difference between this and the strong acid is that notice right here, this shape right here is different. The increase is a little bit not as steep. I mean, sorry, steeper, right? The increase is steeper, right? And the increase is steeper to the equivalence point, such that the pH is now going to be above 7 when you get to the equivalence point. But then after that, it actually levels off like it is in strong base. There's no difference with a strong base, right? So calculating pH when some weak acid is neutralized, right? You can start out with the solution containing the weak acid. You can add some strong base, right? So that's the example that we just showed a second ago, right? In this neutralization reaction, of course, the acid decreases and the acetate or the conjugate base increases. And so this is the equation you'll have. You'll have the HA plus the OH minus makes the conjugate base and the water. Now you can go through and calculate all the new values using the ICE table, the modified ICE table, not the one that has the equilibrium, but the one that says before and after, right? And then you'll get the pH from that, right? So calculate the moles of weak acid, calculate the moles of the base, and then the moles of the anion formed, and subtract it from the mole of the acid to see how much acid is left, and then use the Henderson-Hasselbalch to find the pH. So those are the steps. So this is just reiterating the fact that it's never going to be that easy. We're never going to give you just the number of moles. It's going to be a concentration. You'll have to figure out the number of moles yourself, which is easy, okay? And so, right, um, so in what ways does a weak acid titration differ from strong acid titration, right? And you can be guaranteed that I'll ask you this question on the exam or on a quiz, right? Which of the following is different between a titration of a weak acid and a titration of a strong acid? Well, the first thing is that titration of weak acid, the first thing is that the solution of weak acid has a higher initial pH than a stronger acid, right, than a strong acid, right? And then the pH near the pH near the equivalence point is smaller for a weak acid, so this is at least partially due to the buffer region. And then the pH at the equivalence point is greater than 7 for the weak acid. So here's your next question. Which of the following is not true about the difference between a weak acid and a strong acid titration? A solution of weak acid has a higher initial pH than a strong acid. The pH change near the equivalence point is smaller for a weak acid, at least partially due to the buffer region, right? And then the pH of the equivalence point is greater than 7 for a weak acid, or all of these are true. So what do you guys think? Yes, it is D. It is all true. All those things are true. But I might change something. For example, I might change it to a lower initial pH in a strong acid, right? Or I might change it to a bigger equivalence point is bigger, right? And stuff like that. But all these are true right here. Okay, all these are true. All right, so the use of indicators. So the indicator that you used back in the indicator that you used back in the lab last week, right, was phenolphthalein, which turned pink upon basicity, right, or alkalinity, right? But what exactly are indicators? Indicators are actually weak acids that have a different color from their conjugate base form, right? So the conjugate base form, for example, uh, for phenolphthalein, right, its conjugate base is pink, and that's why it turns pink when most of it turns pink, or most of it becomes basic, right? So that's pretty cool that you can actually lose a proton. You can begin clear, right, but then you lose a proton, and what happens? You turn pink. It's kind of neat, right? So each indicator has its own pH range for whichever it changes color, right? And an indicator can be used to find the equivalence point in the titration, as long as the color in the small volume region, rapidly changes, where it rapidly changes, right? So because you want to make it so that the indicator has a very similar kind of titration curve as what you're titrating. Okay. Oh my God, what is all this white stuff? Is this like chalk? What is this chalk? Nasty. Anyway, good thing we're wearing masks. Otherwise, I'd be sneezing. So, Here's some indicators, right? Here's phenolphthalein right here, and its color change point, right, is right here. Okay, so that's pretty good because that's where you want to see the equivalence point right there, right? We also have another one here, right, called methyl red, and it's it uses you can use this also for strong acid, strong base, and its color change happens here at a little more acidic, right? A little more acidic. Uh, so here, this is very reminiscent of a weak acid, strong base, right? And I don't even know. Yeah, so that's also phenolphthalein right there, right? And the great thing about phenolphthalein is that its color change region is exactly where we need it to be for the weak acid, weak base, right? Equivalence, right? And then over here we have methyl red, right? And again, the equivalence point here is up there, but the color change region is down here. So this is a poor choice, a very poor choice for acetic acid or a weak acid, right? Because you want the color change to happen over here, with the color change to happen where the equivalence point is, because that's where you need it to be to actually see it happening, right? To see where the endpoint is, right? So when doing a weak acid like acetic acid or something like that, titration with a strong base, phenolphthalein is good, but methyl red is bad, right? Methyl red is bad. So this is just zoomed in right here, right? Zoomed in. Here we see the no, it's not a zoom in. This is a different one. Okay, so here we have the equivalence point for whatever this acid is. I don't know what this acid is. I'm not sure what this acid is, but uh, for this particular acid, this titration curve has the equivalence point here in a more acidic region, and so phenolphthalein is bad for this, right? Bad indicator. But now we can use methyl red because methyl red has a good color change right there, exactly in the middle of where the equivalence point is. So for this, whatever this acid and base titration is, methyl red is a good indicator for that. And there's many different indicators you can use. One that we did back in high school was cabbage water, right? Red cabbage water. So that's a good time. And you can actually make a rainbow of colors with cabbage water, I think. I think that was cabbage water that we did that with, depending on the pH. So the thing I want you to know about this, I'm not going to ask you on the exam to actually calculate any Kas or concentrations using with polyprotic acids, right? But basically, a polyprotic acid is an acid that has more than one proton it can lose. But the thing that I want you to know about polyprotic acids that's very important is that when it loses its first proton, it has one Ka. When it loses a second proton, right, it has another Ka, right? So it has multiple Kas. Okay. So the number of Kas it has is based on the number of protons it can lose. So if you recall back to the problem that I gave you in discussion section 2 weeks ago, where we had phosphorus acid, right? That thing had 3 protons, but only 2 of them were actually acidic. So how many Kas does it have? How many pKas or Kas does it have for phosphorus acid? Since it only had 2 protons that are acidic, even though it has 3 protons in the formula. 2 of them, exactly, right? So that's something I want you to know about polyprotic acids. I just need you to know that the number of protons that are acidic is equal to the number of Kas it has, right? And then the highest Ka or the lowest pKa will be the one for the first proton, and then so on, right? All right. So, which of the following is not true about indicators? Indicators are strong acids that have a different color. Each indicator has its own pH. An indicator can be used to find the equivalence point, or all of these is true. So what do we think the answer to this one is? Yes, that is exactly right. It is A, because it's not, indicators are definitely not strong acids, they're weak acids. Good job. So that takes us to the last part of this lecture, which is solution or solubility equilibria. Okay, I know, right? We had chemical equilibria, then we had acid-base equilibria, which we spent the last few days on that, And the very last thing we need to talk about now is solution equilibria, okay? So the thing about solution equilibria, right, is that it has a different letter, different constant. So remember that remember in chemical equilibria, the equilibrium constant was Kc for things that had concentrations, and then the equilibrium constant was Kp for things that had pressures, right? And then the equilibrium constant for acids is Ka, right? And then the equilibrium constant for bases was Kb, right? Well, now we have the solution constant, or the solution solubility product constant for solution equilibria, and it's Ksp, okay, Ksp. So the thing that we need to know here is that this is based mostly on ionic compounds, right? Like sodium chloride, things that are ionic salts and stuff, right? And those are extremely strong electrolytes, and so they will completely disassociate in water when they dissolve, right? They will completely disassociate. So when an equilibrium equation is written, the solid is the reactant, and the ions are going to be the ions in solution are going to be the products. Kind of like when we were doing acid-base equilibrium, we had the acid as the reactant, right? And then the conjugate base and the conjugate acid as the products, right? But here it's going to be the solid as the reactant, and then the solution ions will be the products, right? And we can make that equal to Ksp. And this one's much easier because there's only two things. Take, for example, we have barium sulfate solid right here, right? And in this equation, barium 2 or barium 2 plus, right, disassociates to sulfate 2 minus, right? And so to do the Ksp equation, it's quite simple. It's Ksp equals barium sulfate concentration times the barium concentration times the sulfate concentration, right? Cool stuff, right? So again, though, just remember that coefficients in the balanced chemical equation represents what in the equilibrium equation expression? It represents those exponents, right? And so, for example, now we have something like barium phosphate, right? And for barium phosphate, you need 3 bariums for every 2 phosphates. So when they separate out, right, the coefficients actually, the subscripts become the coefficients. So you have 3 moles of barium, and you have 2 moles of phosphate, right? So of course, this 3 right here and this 2 right here for those 2 ions become the the exponents in the equilibrium expression. So now Ksp equals Ksp equals Ba to the third, right? And then PO4 to the second, right? So it's the same thing as it was with chemical equilibria and acid-base equilibria. The coefficients become what? The exponents, right? So just to be clear though, Ksp is not the same thing as solubility. Solubility is the quantity of a substance that dissolves from a saturated to form a saturated solution. So the common units for solubility, of course, is grams per liter or moles per liter. So, like for example, you can look up sodium chloride in Wikipedia, right? And it will say solubility in water. And I think that sodium chloride solubility in water is like 36 grams per liter, or maybe, yeah, I think that's right. I can't remember the exact number. Correct me if I'm wrong, but that's what you usually see that as. You'll see that as some kind of like salt per grams per liter, right? Some kind of salt grams per liter for solubility. So solubility versus the solubility product constant, or the Ksp. We got the grams, the mass of solubility of a compound, which is grams per liter, right? So like I was saying, I think that sodium chloride's solubility is 36 grams per liter. It could be something else, but I think that's what it is. Okay, and then uh, you can take that with the formula weight, and you can get moles per liter there. And then from that, using its empirical formula, right, for sodium chloride, it's just NaCl, right? You get the molar concentration of each of the ions, and then from that, you can do the Ksp equation because you just put the Ksp equation equal to the concentration of the moles of the concentrations of sodium times the concentration of chloride, right? So, which of the following is not true about solution equilibria? Because ionic compounds are weak electrolytes, they dissociate to a small extent when they dissolve. When equilibrium equation is written, the solid is the reactant and the ions of the solution are the products. The equilibrium constant expression is called the solubility product constant, or all these are true. All right, so anybody got any guesses? What's the answer to this one? It is A. In fact, it is A. Ionic compounds are definitely not weak electrolytes. What are they? Strong electrolytes. Good stuff. Good stuff. Okay, so here's an example of a question that I might ask you, right? I'm going to ask you, for example, what is the KSP for calcium fluoride when it's oh, sorry, let me say that again. What is the solubility of calcium fluoride if the KSP is equal to 3.9 times 10 to the negative 11, right? So what is the solubility of calcium fluoride when its KSP is 3.9 times 10 to the negative 11? First thing you gotta do is write out the equation as always. We have calcium fluoride, which is a solid. It becomes calcium, and then fluoride, two fluorides, right, in aqueous solution. So KSP then equals calcium fluoride, calcium times fluoride squared equals 3.9 times 10 to the negative 11, right? So you have this little equation here. It sure does look like those Ka equations we have to do, right? And so, again, I have to use the ice table, right? Now, at the very beginning of the ice table, we have here calcium fluoride, right? And remember, when it's a solid, you don't have to put anything there, right? And then initial concentration of calcium is 0. And then remember, you have 2 moles of fluoride, so that's also 0. But what that means then is that when you have a change, all this stuff is still 0 for the solid, right? But when you have to change, you only have 1 mole of calcium, but you have 2 moles of fluoride, right? So it's going to be plus X here, plus 2X here. Thus, the equilibrium concentration of both of those ions is going to be X and then 2X. So not as complicated as the acid base or the chemical equilibrium, right? So then you just put it all together, right? Where you have 3.9 times 10 to negative 11, and that equals X times X squared, sorry, times X times 2X squared, right? Because remember that the 2 from the coefficient becomes an exponent, right? And so you just combine like terms and you get 4x squared, right? So what do you do now? What do you do when you have a cube, a 4x cubed rather? What do you do when you have a cubed? How do you solve for x when you have a cubed? Yes, exactly right. Divide both sides by 4, then you get x cubed, right? And you do the cube root of x, right? And if you don't know how to do cube root of x, you should have a button on your calculator that looks like a square root like this, but then above it it has an x in it. And that's how you should do a cube root, right? And so it'll ask you what the x should be, and then you can do the cube root. Okay? At least the calculators I want you to use in the exam have those, right? So quite simply then, right, these are a lot easier than doing chemical equilibrium questions, right? Because now you have x, and then you want the answer in grams per grams per liter, because that's what most solubility is listed as. So all you have to do is multiply by its molar mass, right? The molar mass of calcium fluoride times that, and you'll get 0.016 grams per liter. Neat stuff, right? Neat stuff. Neat stuff. So there's factors affecting solubility. Um, And so here, right, here's pure water, right? And then the molar solubility of calcium fluoride, right? And the concentration is sodium fluoride, right? And notice that the solubility of calcium fluoride decreases sharply as a common ion is added, right? So the common ion here is fluoride. That's the common ion with the calcium fluoride, or the fluoride and calcium fluoride. And when you're adding calcium fluoride to a solution that already has fluoride in it, that common ion makes the solubility decrease sharply, as they say in this slide. Okay, so let's try this now. What is the molar solubility of calcium fluoride in 0.01 moles of calcium nitrate? So now the common ion is calcium, right? So you know it's going to be different because it's calcium. So same as before, make out your equation. Calcium fluoride becomes calcium plus 2 fluorides. KSP equals the calcium concentration times the fluoride concentration squared equals 3.9 times 10 to the negative 11, which is the KSP for calcium fluoride. By the way, KSPs are actually found in a chart in your book, right? But we'll give them to you on a test or something. You don't have to look it up in the book, right? So what do you do now? Again, what you have to do is you have to make the ice table, but instead of having all the same stuff as you had before, you start out instead now with the initial being 0.01 for that extra calcium instead of 0 like you had before. So now it's 0.10 plus X and then 2X for the fluoride, right? And then you put it all together again. Now it's 3.9 times 10 to the negative 11. That equals, excuse me, 0.01 plus X, right, times 2X squared. And again, this is another you're welcome moment. You can assume that this plus X is tiny and drop the plus X, right? So now it's just going to be 0.01 times 2x squared, and that's easy. Just multiply this together, divide both sides, and then square root, and you get the x equals zero point 0.1 times 10 to the negative 5 molar, right? And then to get the grams per mil or grams per liter, which is what we use to say what the solubility is, multiply by its molecular weight, right, of calcium fluoride. Okay. So yeah, that was a you're welcome moment right there. By the way, you guys didn't clap or anything, but I'm playing. I'm playing. Anyway, so yeah, just remember. So also with the solubility product constants, when you have a plus x or minus x, what can you do? You can drop it. Okay. The only time you cannot drop an x is when you're doing the KPs and KCs, right? Which is the chemical equilibrium stuff. But for acid-base equilibrium, you can drop the plus x, drop the minus x. For solution equilibrium, you can drop the x plus x or minus x. Okay. Anyway, so pH also affects solubility too. If a substance has a basic anion, it will become more soluble in an acidic solution. That's just something you got to remember. And remember that buffers control pH. So when the buffer is used, there's no change in the concentration of the hydroxide ion. Right. Another thing, just kind of need to remember. All right, so this is just a picture showing you the effects of solubility when it's pH, right? So here, the salt ions in the conjugate base of the weak acid, right? So solubility increases as the pH increases, okay? And then on this one here, right, salt ions whose anion is the conjugate base of a strong acid, the solubility is unaffected, right, when the pH increases, or with any change of pH, really, right? And so if you have a common, again, if you have the salt ions conjugate base is the same, then solubility increases. But when it's different, then it doesn't even matter. Nothing changes. Okay, so that's just one of those things you got to remember. Okay, so complex ion formations, right? This is not that big a thing, but we'll go over it just real quickly. Metal ions can act as Lewis acids to form complex ions, and then Lewis bases, and then act as Lewis bases in the solvent. So basically, what happens here is you have a metal and and uh, and a whole bunch of things, ions can surround it, right? So, oh, here we go. This part is important though. Okay, so how complex ion formations affect solubility, right? So silver chloride is actually insoluble because it has a KSP of 1.6 times 10 to the negative 10, right? In the presence of ammonia, the solubility greatly increases, and then because silver will form a complex with the ammonia ions, right? So here we have sodium, not sodium chloride, but silver chloride, right? It's a solid right there, right? There's that solid sodium chloride, and silver chloride, and only a couple. There's only one ion of chloride and one ion of silver in there. So most of it is insoluble, right? But then you add in some ammonia, and the ammonia likes to surround the silver. That's the little white balls right there. The little white balls surrounding the silver, and that makes it way more soluble, right? And so eventually you got enough of it in there, right? You get sodium ammonate. I have no idea what that would be called, but not sodium, silver ammoniate or something like that. Is it said in there? Does it say what the name of it is? It doesn't say what the name of it, but it's basically silver with the ammonia as a complex, right? And so it becomes a lot more soluble, right? This is the last thing I want you to do for this test right here, okay? And we'll stop it there. So we need to be able to decide whether or not a precipitate will form, okay? When you add when you have solutes in solution, okay? And so again, we have this thing called Q, right, known as the reaction quotient, and then we can compare that with KSP. So Q, just like it is in acid-base equilibria, right, has the same formula, right, as the equilibrium, the KEQ, right? But remember that the KEQ expression is the concentrations of every component at equilibrium, whereas Q can be any equilibrium, right? Not any equilibrium, but it can be at any time, any point in time. It doesn't have to be an equilibrium. Okay, so that's how it is with acid-base equilibria. That's how it is with chemical equilibria, right? It's always going to be the products divided by the reactants, and that equals Q, right? Uh, but Q, just remember, is at any point in time, not necessarily at equilibrium. Okay, so if Q equals KEQ, right, that means the reaction is at equilibrium. Okay, so the same thing can happen here with KSP. Okay, with KSP, if Q equals KSP, the system is at equilibrium and the solution is saturated. Okay, so whereas in acid-base equilibria, if Q equaled Ka or Q equaled Kb, you had your or even in the chemical equilibria with Kc and Kp, if any of those equaled Q, your reaction was at equilibrium, right? But specifically here in solution equilibria, if Ksp equals Q, then your solution is saturated, right? If Q is less than Ksp, then more solids can dissolve and no precipitate forms. So this would be an unsaturated solution, right? It's not saturated, it's unsaturated. And then if Q is greater than Ksp, then you've reached the saturation point and you're trying to go beyond that and now precipitates will form, okay? But if you heat it up, you can make it a supersaturated solution like those Wonder Packs things that Marla made me buy at the home garden show, right? So those are the things I need you to remember from this slide right here. Q equals KSP means you have a saturated solution. The system is at equilibrium, right? And that system as at equilibrium is true of Q equals KSP, Q equals KP, Q equals C, Q equals KA, and Q equals KB, right? But for this specific one here, the solution equilibrium, it also means that the solution is saturated. If Q is less than KSP, you're at an unsaturated solution, so you can actually dissolve more stuff and no precipitate forms, right? And then if Q is greater than KSP, then you've reached the saturation point and precipitate will form. You cannot dissolve anything else, okay?